Good afternoon, everyone. I still see people every now and then coming in. So I will wait another 2 minutes before we actually start the training, and then we'll really dive in into the training. Thank you all for connecting.
Hey Nikki, how are you?
Good, thank you. How
I,
are
I
you?
thought I would say something, otherwise might be you were talking into the void.
Yeah, okay. Thank you very
I
much.
will also take this step of saying something in this case. Ciao, Thomas, ciao, Nick.
Hello, how are you?
Good. Good, and you?
Good. Yeah, fine. Thank you. Happy you're all here.
Happy to be here.
Good. We can almost start, I think. I'll try to let people in while I'm talking, which is a bit more difficult. So, but in any case, we will have the recording. So let's just start because we have a very full program because I think I have a lot to show. Thank you all for connecting. This is the introduction to the Rat GUI. So again, if you're a user already, this might be too basic, but maybe there's some things you can still pick up. But you're welcome to skip this training if this is too basic for you. There you go. You can all see my screen, I guess. Otherwise, I would have had complaints by now. So this session will be organized with 60 minutes of explanation and demonstration from my side, and then after, at the end, up to 30 minutes of question and answers. If, however, while I'm explaining you have a question, please feel free to just stop me and just start talking so that I can answer your question straight away. I think that would be the most helpful since you're here live. So if there's something that's unclear, please just shout. This training will be a reference material, but we have other reference materials for you, like our YouTube channel. In this training, I will have links to specific tutorials that might be useful for different topics. We do have a manual. I see that I have no link here, so I put the link. It's on our website, but I will also add a link here. In addition, I have tooltips in the node editor of the GUI itself. I will show you those later. And after, if there's any questions, you can always send me an email directly to nikki@ratgui.com because we're always happy to help everyone if you're running into trouble after this training. So quick introduction to Rat. Rat is an open source tool that is used for modeling and simulating of magnets. So it's a software for magnet engineers. It's written in modern object-oriented C++, and it's designed for accurate simulations of electromagnetic fields, inductance of coils, quench protection, particle tracking, and more. It's modular and extendable, and it's open source, and you can download it on the web. But for convenience, we have a user interface, and it's a graphical user interface, and that's why we're here today, which is user-friendly, and you don't need any coding. So everything is visual, and everything that you like to access that is available in the open source Rat library, you can access through the graphical user interface. So on to the training. Rat GUI for modeling magnets. As I said, it's to model the magnets in 3D and to calculate their properties. In Rat, the focus is on electromagnets, so coils, so windings with a certain cross-section. And that's what most of this training will be focusing on, because if you learn how to model your coils in 3D in Rat, then you can also create easily other objects in Rat, like meshes with nonlinear materials, like iron yokes, permanent magnets, or other non-magnetic objects, but they all follow the same basic principles. And those are the building blocks of Rat. So you model your magnet in 3D by taking a path and a cross-section, and you extrude your cross-section along this path, and that's how you get a 3D shape. This 3D shape is fed into the calculator of Rat to obtain, for instance, field maps in 3D or in 1D or 2D, the harmonics for field quality, quench for superconductors, particle tracking, and many more. The results can then be analyzed in the post-processor, a little example you see here at the bottom, but also the results can be exported to process the data in a different format. Since we're talking about the Rat GUI, it's important that I introduce the interface to you first, and that's what I'd like to do now. So the interface is organized in a few sections, and the most important one is probably the model browser. The model browser is where you will have all the objects available in your model, like your coils or your iron yokes, that will all show up here. And in addition, the calculations will also show up here. So the model browser is where you access your coils, where you add your coils. And to do that, you right-click on the model tree in the model browser. Then a list pops up, and you can go here to select an object from the list, for instance, a coil, and then you can click on any of the coils available to add it to your model. And the same thing goes for the calculation tree. Once it's in the tree, like in this example over here, if you left-click on an object in the tree, you will see in the node editor that the settings of the object appear. These settings can just be edited by typing in the boxes or by clicking on the plus and minus signs. And if you hover over the question marks in the node editor, you will get some extra information about what the settings mean. Excuse me. If you, a different way of selecting objects in your model is by clicking on the object in the viewport, which is the part that is here in the middle. The viewport will then be, it will get a different color, the object, so that you see that which one you have selected. And in this case, for instance, the objects are a group of objects, a tree of objects, like the model tree, because this coil that is selected here belongs to a mirror group, because if you see here, there's actually two coils, and the mirror group is actually in a toroid group, and that's this whole circular shape of coils. And by clicking multiple times on the object in the viewport, you will traverse down the tree here and get to the selection that you actually want. If you stop clicking, you will, for instance, add up in the mirror. Then the viewport itself can also be controlled with your mouse. I think most of it is straightforward, but I have a summary of the mouse controls here for you. For instance, if you want to rotate your model in 3D, you left click and you hold and you start rotating your mouse and your model will follow. You can zoom by scrolling. If you haven't got a scrolling wheel on your mouse, you can right click and drag vertically, then you will zoom. You can pen or move the model by holding the middle mouse button or by clicking Shift on your keyboard and left click and dragging. Then you can also move your model. You can change your camera target. That's quite a nice one because it will point the target of your camera at a different location in your model, and then you can zoom into a specific part. And by default, we have perspective projection. So things look like in real life. So objects that are close will be bigger than far away objects. But you can actually also change to orthographic view. And in that case, your view lines will all be straight. So objects that are behind some other objects you can't see anymore. But it can be useful in some cases. Now, let me actually demonstrate this by looking at the Rat GUI itself. So I'm assuming again that you can see this, otherwise I will hear you. So here I'm with my mouse clicking and rotating and zooming the model in 3D. So like I said, here you have your model tree. And if I want to add another object, I right click. Here is some extra hints. In the GUI, I right click on model tree, add coil, and I say racetrack, for example. And then you see here the new racetrack popping up. Now I click on it and I can then edit everything here. You see the length changes, the radius of these. This is probably a bad example because the toroid is still in front. Anyway, the point is probably clear that by changing the settings over here, you can actually change the shape of your coil. Same thing goes for calculation. I right click on calculation tree and I go to add calculation to add, for instance, a plane calculation. And then this little green line of this plane will actually give you an indication of the plane that you are going to calculate your magnetic field on. And you can also change settings of this plane by selecting, by selecting it in the model browser, and then your node editor will have the settings of the plane calculation, and you can offset it, for instance, by 100 millimeters. And if you want to do the actual calculation at the bottom here, you press calculate, and then it's performing the calculation. This looks a bit funny because I'm giving you a crappy example here in the view browser, but I think you get the point. In this post-processor window, you will see your results. In this case, it's the magnetic flux density. And with the settings over here, you can actually make your plot look different. You have some, for instance, the vector plot, so you can have these arrows to indicate the field direction and so on. You can drag your axis. Also, this one you can drag to change the color scheme a little bit. And by right-clicking on the axis, you get more options that you can change. You can export your data also to CSV or VTK, and VTK is meant for ParaView. I will not go into details there, but we do have tutorials on our website, on YouTube, where ParaView and Rat together are explained. There's another thing that's nice in the GUI. If you click on a window, you can drag it, and then you can actually paste it to somewhere else in the GUI. And that goes for everything that's in the GUI. So I can also move my node editor somewhere else. This is probably not the best example, but I can also, if you want your model browser and your node editor sort of together, then like this, by clicking, holding the mouse button and dragging the mouse button, you will see these blue boxes appear, and then you can move your window. Other settings can be found here. So you can change the theme. If you want to make pictures for your report or you just prefer white, you can choose that. You can change the GUI to have a different font, smaller, which is for today not very convenient, but it's possible. That's maybe a bit too big. There you go. The units, that's a nice one actually, because as you can see here in the node editor, the units, for instance, in size here are now millimeters. So everywhere that there's a unit involved, you will see that here. Please make sure to keep a note that if you hover over these question marks, you get more explanation on what the settings mean. But if you go to settings and go to units, you can also change the length to meters, for instance. If you have large coils, that might be more convenient. And we have units for everything. So you can change the settings here. Model scale has to do with sort of the default size of what your objects will be. So if, in this case, I've selected decimeters, which if I now add a coil like a solenoid, that will have a radius. I'm going to change my settings again, the units, because that's easier to show. This is now 50 millimeters radius, which is like 100 millimeters diameter, which is like a decimeter. So that's the sort of default size of objects that will be added. It's not very important to change that, but you could. The max editor depth, that's actually interesting. I'm going to start again. There's many examples here. If you click on home, start from example. So I'm going to start by going back to this mini toroid, and I'm going to change things back to classic because that's what I'm used to. The setting max editor depth, if you set that to 0 and you click here on toroid, you will only see the toroid settings in the node editor. You can change to mirror by clicking here, but you can also change your max editor depth to 2, and then the levels down the tree up until 2 will all be visible here in the node editor. Tools will be the simple things like copying and pasting. So in the model tree, I can copy Ctrl-C and Ctrl-V, and now I have 2 toroids. If I need to kind of change those, there you go. And now you actually see them. So all the normal things like copy and pasting is there. View is interesting. Here's your orthographic view. If you're interested, you can look at these yourself. But one that's important is toggle mesh, because this allows you to see your mesh size. Now you see these squares here, which are your mesh size. And if you look at the coil, settings that are DLM or DELM or something like this is always the element size. And you see now that when I change that, the element size changes. And if you want to inspect your element size, you can do that by View, Toggle Mesh. I will now turn that off. Home is where you start the simple things, open model, save model, and so on. Very important, we have lots of examples. So home, start from example, and then you can start to do your examples based on that. You can sort of play with these and then see what the units, what they do if you're not sure how to start from scratch. So I'm gonna close these now. Back to the slides. So modeling in Rat, because that's the most important, because once you have your model, I will show you how the calculations work a little bit, but most of the calculations speak for themselves. Modeling, however, is something that is what you will be doing most in Rat. You want to be able to make your own custom shapes, and that's why I will focus on that right now. There's 4 types of objects in Rat. You have the coils, which are objects that can carry current and have linear materials. So electromagnets, they can be, it doesn't matter the material. Basically, it just takes the location of the current and based on that calculates the magnetic field. They cannot be things like iron. That's why I'm saying linear materials. Meshes are objects that cannot carry current. You can use those, for instance, to draw your support structures. HB meshes are objects that can be magnetized and they could be nonlinear materials. So this can be an iron object, HB mesh. It cannot have current. And then there's permanent magnets in Rat, which is an object with a constant magnetization and no current. And you add all of those in the model tree by right-clicking on it. And then here is the list of 4 things that you can then select. In Rat, for all of these, you have predefined shapes like your solenoids and your racetracks, and you have custom objects, and those are the more interesting ones. Predefined shapes have their specific settings, like a solenoid has a radius and a thickness, but custom shapes, their settings are defined by the settings of the path and the cross-section. And so the predefined shapes, that's a nice one actually. This you should keep in mind that if you start from a solenoid, you can always go back to the basics, to their path and their cross-section by right-clicking on them in the model browser, selecting edit node and then split. And then you will see that your solenoid has become a path and a cross-section. I will demonstrate that quickly. So right-click, edit node, split. And now instead of this solenoid, which Ctrl Z, solenoid has these settings, radius, thickness, height, right click, split. Now I have the rectangle, and so I can change the rectangle instead of the height, and I have the circle, which only has a radius. So if you have a simple shape or like a predefined shape and you actually want more freedom, you can go back to its original by splitting the object. Modeling in Rat, again, is done by taking a path and a cross-section, which forms a 3D shape. And then you can sort of pretend like your cross-section, that would be the shape of your conductor. In this case, it's a rectangular conductor, but you can also have like round wires if you want. And the path would be the windings of your coil. But any object, so also the HB mesh and the normal mesh, any object in Rat can be created as a custom object, and that always means that you take a path and a cross-section. The orientation here is a little bit important, especially if you are going to do more custom shapes. We have 2 coordinate systems. One is the local one, and that's mostly how the cross-section is defined in the N and D plane, and the L vector actually shows you locally the orientation of the path. So that's the direction basically at that point where the current flows, in which direction the current would flow. And this whole object is then in 3D space just in your normal XYZ. L is for longitudinal, N is for normal, D is for transverse. And keep in mind, due to legacy reasons, it's a left-handed system, the local one. I'm not sure if you need this very often, but if you want to take full advantage of the custom features in Rat, it's important to keep in mind the local orientation. And so in the case of a solenoid, the conductor path would correspond to the longitudinal coordinate. So that's the direction that the current flows in. The radial direction is corresponding to the normal coordinate, and the actual direction of the solenoid is the transverse direction. And this is important not only for how your path is defined, but also your cross sections, because in the settings in Rat GUI, you will always see that if you start using a cross section, they are defined in N and in D. So then you know where it comes from. So let's continue with cross sections, because now I have assumed that we have started building our first custom object. And when you do that by right-clicking and adding a custom coil, you will first see that there is a bit of an error. And if you hover over this orange color, you will see that it's asking for an input path. So let's do that quickly. I will just, for demonstration purposes, take a circle, but it's still unhappy because we also need a cross section. So I right-click on custom coil. So I've added my custom coil by right-clicking on the model tree. And if I want to change the settings I want to add my path and my cross section to the custom coil, I right-click on custom coil, set cross section and rectangle. And there you go. Now it's happy. There is a custom circle. So cross sections, we have a few standard ones, simple ones that don't need a lot of explanation, like a point or a line. These two can be used in case you want to model your coil or you want to represent your windings. Since you have a circular cross section by just a point in the middle, that's fine. But in most cases, you might want to add like a rectangular shape or a circular shape. Or a wedge, and those things I imagine you can sort of imagine what they would look like. And as you can see here, the settings are defined in the normal and the transverse direction. And you can choose also, therefore, to either place your cross section, because the path will also always go in the origin of your ND plane. So you can choose to extrude your cross section with the 0 coordinates in such a way that the path will be going through the corner here. Or if you want to center your rectangle on your path, that's also possible. And then you just change your N and D coordinates in such a way that the 0 of the cross section is in the middle of your rectangle. There are more special cross sections, and one of them is the cross group. And this can be nice if you have maybe 4 wires, always 4 wires close to each other. I made here a strange shape. It's just for demonstrations. So what you do in that case is you right-click and add cross section. You select group, and then you can, let me actually do that. I right-click on coil, set cross section, group, cross group. And now it's yellow because we need to have cross sections inside this this group. So this is a way to make an even more interesting looking cross section. This one is wrong, and the reason for that is because now my 2 cross sections are still overlapping. So if you're going to do this yourself, you need to change the radius a little bit and your wedge in such a way that I think this would actually, no, this would not work. -20 to -10. There you go. Now they are not overlapping, and that's important in the cross group, because if they're overlapping, the current over here is doubled, and you don't want that. So then your field will also be not the field that you're expecting. Another one is the cross group. So what can it be useful for? For instance, U-channels, because here, if you take like 3 rectangles, you can form a U-channel. So you can make them touch, not overlap, but you can make them touch, and then you have a U-channel. A special one, which is something you might want to use way more often, is the dist mesher. We do have a YouTube tutorial on the iron solver, and that's where I explain the dist mesher. But basically, you can use this to add and subtract 2-dimensional shapes in such a way that you get even more special shapes for your cross section. You can add them together like in a union, You can also make a sort of U channel, or you can make a sort of an eye shape, and that's what you use dish measure for. So please watch the tutorial if you want to know how to do that. I have a slide here as well. I will send you the slides, but I would like to tell you a lot more, so I'm gonna skip this one for now, since we have a tutorial. The last one is nice. It's a cross path, and this is used to create tubes and shells, like you see over here. And what you then do is you add a cross path, and then it's asking you to set a path, like a circle. And now, the circle needs to be smaller. If I now look into this, so there is a special group here called clip. I will talk about that in detail later. 0, 1. Where's my clip? I don't see the clip. 0. Oh, God. There's an offset. I feel like I'm doing it wrong. Anyway, create coil custom set path, whatever, circle. And we had our cross path with a circle inside. This circle should be smaller because when we look inside, we should have a tube. There you go. I don't know why it went wrong the first time. I probably clicked in the wrong direction, but this is now a cross section that is more like a tube. So that's what you use the cross path for. So let's go and look at the paths, because now we know what the cross sections can look like, but we have many different paths as well. This is the second part of your custom coil. And many of them I don't think I need to explain, because we all know what a rectangle and a trapezoid are. Just make sure that you right-click on Custom Coil, Set Path, and select one from the list here. I will go over a few more special ones. This one, the first one, is for accelerator magnets. It's a cosine theta path, but we do have a tutorial on that. So I invite you, if you would like to create one of those, to have a look at the tutorial on YouTube. And it's just important to know that it's based on the definitions given by Stefan Ruschenschuk in his book Field Computation for Accelerator Magnets. So if you want to have a cosine theta coil, then please look at this tutorial for more information. We have lots of options for the CCT. So this is a different type of often used for accelerators magnet. And this is actually probably one of the most flexible shapes that you can create in Rat, because you, first of all, you have two versions. Like a regular CCT, this will be a more standard one, and it has only one harmonic, so you can only create a dipole, or just a quadrupole, or so on. Or a custom CCT, and then you can have multiple harmonics along the length of the coil, and you can even change these harmonics as a function of length. And the way you would do that is if I remove everything here and I add a coil custom, I take a rectangular path for my cross section and a custom CCT. Now it starts as a solenoid because I need to add a harmonic to it. So I right click on custom CCT, add harmonic quadrupole. And then if I change the angle of the quadrupole to, for instance, 40, you already start seeing your CCT shape. Now you do need to make sure in your custom CCT that your spacing between the turns, there you go, is large enough. And of course, I also didn't take care that my cross-section is small enough, but you can see where this is going. Now, this only has a quadrupole, but I said to the custom CCT, you can add more than one harmonic. And so here I add a dipole with an angle of 35 degrees. And you see that the shape has now changed. And this CCT has now not only a quadrupole field, but also a dipole field. If you want to check the field, you go to calculation tree, add calculation harmonics, spherical. No, excuse me, of course not spherical. Add calculation cylindrical. Then you can use this path and this axis to calculate the harmonics here on these circles, which you can change the radius of in the node editor. I need to add like a current to this. And probably for a CCT, I want a double layer. Layers 2 that are not on top of each other. Oh, there you go. This is a custom CCT. And if I now calculate the harmonics, there you go. This is all live, so this is your calculation speed for you. I'm running on a MacBook Pro. So here you see there is a dipole component, and also in the this is the normal harmonics and the skew harmonics. You also here have the quadrupole component. So that's a custom CCT. There's many more things you can do to the CCT, but for the sake of time, I'm gonna have to move on a little bit. Another nice shape is the clover leaf. Here, if we add like the clover, if we start from, we start fresh. And if I add like a coil clover leaf here, this one has all the explanation of what all the settings are right here in the node editor. Not for the separate path, but it is in the clover leaf coil. So that is something you can probably look at on your own. Because we do have a lot of things that are predefined for you. There's many paths here, like CCTs, flared end coil. There's many things that you can actually already create in Rat. But obviously, I chose the wrong example. So there's many paths that are sort of standard already. But obviously not all the paths we can think of, all the shapes we can't put into here. So if you cannot find a path that represents your coil, you can use the XYZ table or file to import coordinates of your custom path in such a way that it will be exactly the coordinates that you want them to be. The file that you import needs to have a header. Doesn't matter what it says. It can say, my name is Nikki, and then this file will still work, because what it does, when it reads the file, it will ignore the first line. So if your first coordinate is on the first line, it will ignore the first coordinates as well. And then what you do need to make care of, that it's a comma separated file. So you have 3 columns, and then you have the X, Y, and Z coordinates in each of the different columns. This is for making a very custom shape path. There is another custom coil that you can also define with these paths. And that is the edges coil. And the edges coil is defined by 4 XYZ files or 4 XYZ paths. And that will allow you to actually also vary the cross-section along your path. So if your cross-section is going outward and inward, and you can define that by 4 edges, you can make your cross-section grow and shrink, but also rotate. So if you have a cable that is rotating along the path, this is one way of doing it. On the other hand, we also have a spiral path and a map. So one of the tutorials on YouTube is actually how to map a spiral path on an existing path. And then you can actually have, you can have also a rotating and twisting cable. There you go. Next, transformations. So now that we have our sort of base shape, we might want to transform them. Like if we have multiple coils, we want to be able to translate one with respect to the origin of our model. We want to rotate some coils with respect to each other, maybe make a reflection or make a reverse, which keeps the normal vector the same, but inverts the others. This basically means that the current direction changes. So if you have 2 coils that look the same, but you want one to have a different current, the current in the opposite direction, you use reverse. You have flip. This will keep the longitudinal vector and invert the others. If you apply this to a coil, so all these transformations can be applied on coils and on paths. So by applying them on a different level in your model, it will have a different effect, of course. And if you apply the flip on your coil, the orientation and current direction stay the same. If you apply it to your path, the current direction stays the same, but the orientation changes, like over here. There's also the bend transformation. This can only be applied to the path, not to the coil itself. And that's okay. You don't need to remember that, because if I have a custom coil with a CCT and a rectangle cross-section, if I click on the coil and go to right-click on the coil and then go to add transformation, bending is not possible. So if I want to bend this CCT, I can only bend the path. Now I can bend it. This is, yeah, you start to see it already. Are we in Z? Yeah. If I make the CCT very long, then hopefully you should be able to see the bending, but we shouldn't bend around Y, we should bend around X. Oh, now I did a lot of bending because my my radius is large. But you see here, you can play with the bending on the path. Axis and direction must be orthogonal. That's important. These are some hints for how to make the bending function work. In addition to transformations, so that will change the shape of your coil, you can also place coils in groups, model groups, and that will allow you to create arrays of coils, angular arrays for toroids, mirrors, but also path arrays. So then the array will not be on a circle or on a straight line, but the array will be on a path. Like in this case, we placed an ellipse path in the path array, and then you get this sort of array. And you can clip. I already demonstrated that a few minutes ago. Clip has no effect. Clip has no effect on the calculation. I think it will calculate even if I clip a solenoid. I will demonstrate this now. It will do the calculation for, yeah, and the reason is clear. If I clip the solenoid, then even if I do a calculation by right-clicking here, add calculation mesh, and I calculate now if this thing has current, I will calculate the magnetic field in 3D. It will calculate it for the full circle because the current needs to go somewhere. So the clip is only for visual purposes. It will not affect the shape of your coil for calculations. That's important to keep in mind. It's just for visual. You can right-click here. This is the processor window, by the way. You see here if your calculations are finished or not. And you can also access data about your calculation, because now I removed the processor window, but can right-click here, go to result. My result is now back. Here I can also do clipping. If I enable Y, there you go. So here I just clip the results, and I can zoom in here to see the field changing, the flux density on the inside of the coil, which might be useful. I will go into calculations more later. These were sort of model groups. Another interesting custom feature in Rat for modeling is the path groups. And you have two options. You either add a path group like in the cross-section group, and then you can add like paths together, or you click on an already existing path and you say create group by right-clicking on it and go selecting create group, and then you place it into a group. If you start from a path group, the paths that you are adding to the group will auto-align. That means the start of the end of the first section in the path will be connected to the end of the other one by default. Let me show you here, because I don't want to confuse you. So I add a custom coil with a rectangular cross-section and a path group. If I now start to see it's yellow because it's expecting sections. So if I add an arc, now it's happy. This is the first part of my coil. If I add another section, like a straight, it automatically is added to the end of the first section. So here I can add another section, like a super ellipse or something, then it starts to bend out of place. But I can even add like a spiral. This looks ridiculous, but you see the point. So you can add paths together here. This is a way to make current leads. Another way is using the connect group, and I have a YouTube tutorial on that. But that's what I mean with auto align. This is the path group. If you start from a path group as your path, but if you want to change the geometry of your path, then instead what you do, and I will remove this. So I have now a simple circular path. If I want to change its geometry, I right click on the circle, create group, and for instance, I say cable, because now I can make 5 turns if I space them. Let me do 10. Yeah, okay. My rectangle is a bit too big, but let's do 20 then. So now I have changed the circle path shape by placing it in a path group cable. This is a pancake coil, but the cable has nice settings that you can also turn it into a solenoid. And then you see that because it's actually wound as a spiral, as a cable now, you have this sort of S shape here, because in real life, you cannot just, it cannot be straight. If I do this, no, there you go. You can turn this off by doing disable increment. Then it will treat this as, yeah, it's probably easier to look at, no, it's the same difference. Anyway, if you don't want to have this increment that takes care of actual physical winding, then you can disable that here. The other settings, I will leave you to it because there's many more interesting things to say. Coming back to the geometry, the path group is interesting because it also allows you to strongly control the orientation of your model, because it will have the start coordinate. It has the start longitudinal. That means in XYZ, in which direction will the longitudinal vector be? And it has the start normal. And if you define those two, you automatically know where the D is going because it's a left-handed coordinate system. So if you want to have full control of the orientation of your model, you can take a path group and you can use this start coordinate with the definition of which direction the longitudinal and normal go in. You can use those to have ultimate control of your model, of your shape. Let's continue. I'll leave this for you to read because of the time. There are some YouTube tutorials here also indicated, and especially for connections. Connections can be used to make attachments and then current leads, but it can also be used to make layer jumps, so to add coils together. And we have YouTube tutorials about connections as well. So I will go and invite you to look at those separately if you need them. So let's go to the physics now, because once you have a model, you do want to calculate things. That's why you do this. So again, coils can carry current, meshes cannot. HB meshes can actually have nonlinear material properties, and permanent magnets have a constant magnetization. Now, how do you add that? Every coil has physics settings in the node editor. Let me show you. Coil is the higher level object. So if I click on that here, I have physics settings. So the other settings here are more for shape and geometry, but the physics settings will allow you to set a current, set a temperature. Temperature is not really needed unless it's a superconductor. So if you're not bothered with superconductors, it doesn't matter what you put as temperature. These two are more related to the physics of how you calculate the magnetic field. So bio-Savart, basically. The explanation for that is also in a YouTube tutorial, but this is the most important. So the coil you have physics settings for. Number of turns, in this case, I can add my number of turns by changing the cable, right? So if I change, now I have number of turns. But if I have a solenoid, this is a perfectly fine solenoid. or like this. This is a fine solenoid. If this solenoid in real life, very often this would be a good enough thing to calculate your field from, but the coil needs to have a certain amount of turns. So it needs to have current, and there's no turns here. So you need to also make sure that in this solenoid there are X amount of turns, because otherwise your magnetic field doesn't make sense. So if you do it like this with your first we have to split. And then we can create this back into a cable by, oh, my rectangle is now huge, of course. And this also -2 to 2. If I go back to creating this into a cable and I put 100 turns with correct spacing, then your turns are taken care of here. If you leave one turn and you go back to your solenoid, Ctrl-Z, Ctrl-Z, oh, this is not the best idea. If you go back to your solenoid, then if this is actually 100 turns, then this is where you put it, because then in your mesh calculation, it will take care, the magnetic field makes sense because you have taken care of the number of turns in the shape. Source type, target type, softness, and Gauss are important, but they are on YouTube. So for the sake of time, that's where we will leave that. Meshes cannot carry any current. You can set temperature here. And in case you do, so I'm going to add a mesh. This is if you want to add like a support structure. So here I have a simple cube. And if my cube, oh, this one doesn't even have temperature anymore. Fine. Maybe that it used to have temperature. I thought meshes could have temperature. Okay, not anymore. Well, it doesn't really matter because there's no transient calculations in red, so there will not be any temperature flow anyway. But now the solenoid has a temperature of 10 Kelvin. In my mesh calculation, if I go to physical property and temperature, that's what you will see. But in addition, if I add a material property like an LTS cable, and I set this back to 4 Kelvin, and I now do the calculation again, I can actually plot the temperature margin. This is a bad example because the field is so low. But based on the magnetic field, let's see if we can do something about that. Based on the magnetic field, yeah, it's still a low field. Anyway, the point is, since it has superconducting properties, based on those properties, it will calculate the temperature margin. You can look at the properties by clicking here. You will then get all these properties like specific heat, thermal conductivity, resistivity, but more importantly, N value and engineering current density. So this is actually the critical current. And maybe I should have used a different one that looks more. Let's take an HDS tape. Here, I guess this is a very familiar plot if you're working with HDS. And then based on these HDS properties, now I will have a very high temperature margin because I have an HDS tape. So see, it's 80 Kelvin temperature margin. That's because my field is so low. Anyway, HB meshes, again, there is a YouTube tutorial, but the most important part there is that they have a non-linear, let's take a sphere, because I want to just explain to you that there is an HB curve associated to it. So you can create any shape, but what's important is that an HB mesh has an HB curve. In this case, we have a few standard ones like this one, but you can right-click here, add HB curve. And if you have a file or an HB table, then based on those, based on the file or on the table, you can create your own HB curve. Let's see what else. And permanent magnets have a constant magnetization. And when you add a permanent magnet, like a bar, you can here in the node editor set the, let me just throw this one away. Here's your bar. You can set a constant magnetization in 3 directions defined in longitudinal, normal, and transverse. At the moment, in Rat, we have no way of having a non-constant magnetization. That's on our to-do list. Calculations, the last bit. The calculations in Rat are nice and speedy because they are based on BioSavart that is accelerated with the multi-level fast multipole method. The algorithm used is sorting the sources and targets that normally would be used by BioSavart in groups, and this it does that in a smart way, and that allows you to speed up the calculation massively because you do not have to calculate the field from each source on each target, but you only calculate the field for groups of sources on groups of targets. That's illustrated here, but more importantly, we have detailed explanations on how that works in YouTube tutorials. For the iron solver, it works a little differently because what it does, it first, for the electromagnets, because you need to have some source of magnetic field in order to magnetize your iron object, for instance. It uses BioSavart with MLFMM, so with the multipole method, to calculate the field from the coils. It calculates this field on the target object, so also on the iron. But then first, it calculates this field on the iron, so on the target points. Then based on that field and the HB curve that you have defined in your settings, the iron solver is on, so the magnetization of iron is calculated. And this is based on a volume integral method, which is nice because it's fast because you don't need to mesh the air, basically. And then finally, the field from the iron object is calculated back onto the target points and is basically added. So the field that this produces is then added again to the everywhere else in the mesh. How do you do a calculation? I already demonstrated this, sort of. You do that by right-clicking on the calculation tree and adding an object from the list. It's important to know that everything you see in the view browser, so if I start again from my mini toroid, everything I see here will be taken into account by the calculation. So you don't need to tell it separately that you don't need to tell the calculation what to do. If this is seen in my viewport, the mesh calculation will be for all these coils. If you don't want to include everything in the calculation, but you want to keep your model, you can right-click on an object and say enable. Then it stays in the model tree, but it is removed from the actual model, basically. And then if I do the mesh calculation, it's no longer there. So as long as it's in the viewport, it will be included in the calculation. You don't need to do anything special in the case of iron. If the object that you have at HB mesh is an iron sphere, then the calculation will automatically, it will take longer, but it will automatically do the nonlinear solver. So that's what it's doing right now. And here you go. So now this is not great for visualization purposes, but this iron sphere here is now used in the calculation here. And you don't need to tell the calculation basically that there was an iron object, because it knows from the fact that this is an iron, the HB mesh, that it needs to do the iron solver. When you add a calculation, you will have a visual representation in the viewport. That's what I already mentioned in the beginning. So that's these, not for inductance, not for mesh. Blah, blah, blah. So that's these like path. This line here is the path that you will calculate the field on, the plane here, and so on and so on. If I right click here, I get all these options. So point, line, path, plane, and mesh is all, and Cartesian grid and polar grid is basically all calculate the magnetic field onto a shape. And the shape is either a point, a line, a path, a plane, a mesh. Mesh means every mesh visible in the viewport. A grid is 3D, so that's a box. I can do that calculation. And the polar grid is like a polar grid. So it's not a box, it's in this case, it's a cylinder. And so now I've calculated the field in 3D with this iron sphere in here. I get all my data in the post processor, but again, sometimes it's more useful to export it to VTK and do post processing in ParaView or export it to CSV. What you will get in CSV is a file that has XYZ coordinates and then BX, BY, BZ. But also, since we have the field types, all of these field types here, like not just the vector potential or the magnetic flux density, all of these 4 will actually be in your data file. You can also split them in components. So if I plot the X component now, it looks a bit funny because there's not really a lot of field in the X direction in most of this. Maybe I should have plotted the Y component. No, the C component. There you go. Yeah, this is also the worst example because it's a 3D grid. There you go. Let's go back to the mesh. Maybe I should remove my sphere. Anyway, if I now plot, this is the magnetic flux density. If I go to settings, field component, and I plot the Z component, you will only have the Z component of the magnetic flux density in your 3D plot. There's many things you can do in the post processor, but if you need more, you can export your data and do it anywhere else. Calculations in red. Since the calculations are so fast, they will stay in your memory until they are removed from the post processor. So if I do, I can do this, delete, and now the memory is deleted. I can also clear all, and now none of the calculation results are available anymore. But the calculations are quite fast, so you can immediately get them back by doing this. However, of course, if you make a fusion stellarator, I don't know, 50-meter long coil, your calculation time will increase. Beware that you also change your element size, first of all, because now this is in millimeters. If you have a 50-millimeter long coil, change this to like 50 millimeters or something like that. But the calculation time still scales with the number of elements. In that case, there's no way of saving the data with the Rat model. So if you save your model by saying, say, save model, the data will not be stored on your computer. So the only way to save the data is by saying export to CSV or VTK. So that's an important thing. That's a feature that we don't have yet. And one of the reasons is, of course, it would be much more convenient, but one of the reasons is in most cases, it's fast enough. It is on our to-do list. Multiple windows, same calculation can be opened. I really don't know what I meant by that. Sorry for that. Field on the mesh, I've showed extensively already. Mesh is a very nice one because in mesh, you'll really see the benefit of adding material properties like I did before. HGS tape, whatever, HGS tape. And in mesh, this is really where you have a lot of different properties that you can calculate. That also means like load line fraction, for instance. That also means if you export this data file, you get everything in the data file. So you get XYZ, you get field in XYZ, you get temperature margin in XYZ. Everything will be there in this same CSV file, all these things. If you do not add a material property, that's fine. You can still do the mesh calculation, but then the temperature margin or the load line fraction will be 0 because there's nothing to base that on. But if you're just interested in the magnetic flux density, you don't need to add materials because Rat will just take where the current is, and the current is defined by the shape of your coil, the current location. It'll take that current and calculate the magnetic field. If you want to add materials, lots of it is based on the NIST cryotectic database, but the HGS and LTS properties are, some of them are from the Robinson Research Institute database, others from CERN. Everything is basically from open sources. You can change fit types and parameters, but we don't really have a lot of time for that. Most importantly, if you add material properties, you have more things that you can look at in the mesh calculation. Quench, I do have a tutorial on that online, and I have a lot of slides. So I will send you the slides because the tutorial is slightly outdated, slide, with respect to the current quench calculation, because we used to have only 1D, 0D, but nowadays you can also make it into a 1D adiabatic quench calculation by using enable 1D NZP. And then it will use the material properties and calculate the propagation of your quench based on that on a defined length of conductor. And it will give you more accurate results. So that is hopefully explained well enough in these slides that I will send you. And if that's not the case, please send me an email and I will happily explain that to you. And on my to-do list is updating the tutorial on quench. That's also on the to-do list. So here is where I would like to stop the training. After this training, again, feel free to contact us because I cannot show you everything in Rat right now, today, obviously. So if the tutorials and the manual and everything you find online is not enough for you to understand certain things, please send us an email because we're happy to just help you via email. And if necessary, we can always schedule a video meeting to explain you how to model a certain shape in Rat and how to do the calculations. And that's it for the training. So this would be a great time. If you have questions, I have another 30 minutes. If that's not necessary, then we can stop early. But if there's questions, I would like to invite you to ask them now if you would like. So this is the end for me.
I do have a question, Nikki. So if we do the model of the coil and then we want to run mechanics, when we do the export of, let's say, the force density, do we have also the coordinates of the 4 or 8 or more nodes representing the element that was used to compute the magnetic field?
Yeah, you get in, yes. So let me show you. You will do a mesh calculation in that case, because then in your settings physical property, you will get the force density.
Yes.
Force density in meganewton per cubed meter. And if you export this, you will get XYZ, so the coordinates of the points in your coil, and Fx, Fy, Fz. Yeah.
Yes, but if we want, let's say, the coordinates of the element, and not only, let's say, the barycenter of the element. Maybe you are referring to the nodes, because let's say to do a 3D mechanical model, we would need the coil shape.
Yeah.
To, let's say, subtract it from a former or something like that. Maybe it's the edge.
Exactly. It's probably one of these. So what you could do if you use ANSYS, I think we always recommend people to export it to FreeCAD. Then you can make a step file. And the step file you can import in ANSYS, and together with this force density map, ANSYS will figure it out, I think. Yes. And the other ones, I'm not a mechanical engineer, so
yes, sure.
Yeah,
with
here
all these
are
options, we are going to figure out. Yes.
Yeah, exactly. I think for ANSYS, most people use FreeCAD to make a step file and then import as well the force density table into ANSYS to do that.
Thank you. I have a second question, if I may. For the CCT, you showed how to model the coil. We always have like a circular cross-section, right?
Okay. Yeah, if you want.
Is there?
That's
how
possible.
I would change the cross-section if it's not circular?
Yeah, so I'll start from a new model. So I add a custom coil. Then I right-click here and I say CCT, just doesn't matter which one. And if I right-click again on coil and say set cross-section, circle, now I have a wire. If I actually make the turn spacing, I never use CCTs, so I'm always searching. Omega, there you go. I should probably do this in one big.
Yeah, okay.
Anyway, this is how you would make a circle.
Yes, but I mean the cross section of the former, not the conductor, is still a circle, right?
Ah, you want to have the former.
Yes, let's say if
Yes.
it's a ellipsis or
Yeah, okay. So in that case, you will add a mesh, like let's do what's easiest? A cylinder, I think. No, because that doesn't have a hole. I will add a mesh in the form of a solenoid. Set path circle, and this will be a rectangle. Now I will need to change my circle radius in such a way that it is smaller. I wonder if I have a YouTube tutorial about this. Maybe I can quickly look that up because there's a very nice way that you can make this rectangle. I need to make it much longer, 50. But you want an ellipse. What do you mean by you want this shape to be an ellipse?
yeah, exactly. Because if we want to design a CCT that doesn't have a circular aperture and like an ellipsis,
okay.
We modeled this in the past, but it was just to ask if it's already integrated in the currently version.
Yeah, it's possible. I think it's easier if I either make a tutorial about that, because, okay, if you want to do an ellipse, simple ellipse, I can right click here and set path ellipse, right? You can change this, but I'm not sure if this is what you want, this shape, because you might want to have like a tapered shape. In that case, how did I do that again? I did make that in Rat myself. But that probably takes a while to explain here
No,
on the
that's okay. I
spot.
can
So
drop
it
you
is
a message
possible.
and
Yeah.
Okay.
Yeah, I can send you an example file where I did that, because it's also possible to have like a tapered cylinder, right? Because you want to slide one cylinder into the next one. And so
Exactly.
this taper, that is possible. But of course, now I don't remember how to do that.
No, but that's fine. I will drop you a message to
Yeah.
just discuss. Okay.
I'll send you I can send you a JSON file. So if you save model, it doesn't matter what name, it will be saved as a JSON file. That is the file format that we use in Rat. So if I save this and I close everything, I close and say, yeah. Anyway, I can open the model and then I should look for the JSON file. Then you get the model back. So I can send you a JSON file that looks like, I think is what you want. And if that's not the case, then we continue via email.
Okay, thank you very much.
You're welcome. Are there any other questions about specific shapes or general?
Sure, I have one.
Mm-hmm.
For importing along a curve, you had an option to do like XYZ points.
Yeah.
How many points is a reasonable number of points?
Well, that depends on how large your coil is. So the element size will be defined by the number of points in your file. So for like a circle, oh, excuse me, I'm zooming in too fast. I'm going to toggle mesh here. This is a bit of a fine mesh. I think you're basically asking about how many elements do you need to get accurate calculation results? Or
Yeah, I guess if it sets your mesh size by the number of points, I guess that's pretty straightforward, and I could work off of that. I just don't want to like end up dumping a coil geometry, and it's kind of weird. And
yeah, there isn't. Yeah, so indeed, so basically the number of lines defines the number of points along your path, because every line is an XYZ coordinate. And so more lines means more nodes. In addition, if I go and set path XYZ file, there is this scaling factor. No, maybe it's in the use playing. Line limit. There you go. If you do not have enough nodes in your coil, you can change the element size here as well, in fact. So if you have a very long straight section and then a very interesting curved section, you don't need to have the same number of points in principle in your file, because with this setting, Rat will allow you to cut up the straight line as well. So yeah, I also see a question in the, sorry, is that, is there anything else you would like to ask?
Not yet.
Okay, that's okay. Then I will go to the question in the chat, which is scripting available? No, not yet. So at least not in the graphical user interface. That is something that we would like to add in the future, because indeed, if you have like 5 solenoids, which all have like the same radius, but like slightly different location, it would be nice to set the radius once, but also optimization would then be possible. That is not available in the Rat GUI. It is available on, if you program your Rat, if you program basically yourself. So I'm gonna do this. If you go to GitLab and you go to Project Rat, then in the models, there are different libraries in Rat, and one of them is models. This basically is sort of the umbrella library that does depend on the other ones, but this is where you will actually do your modeling and calculating with. If you go to examples, you have all kinds of examples like cosine theta and so on and so on. So if you would program yourself, then you can just download the code from GitLab, use these models here, these examples as sort of a starting point. And then there is a library called MLOpt, I think. C++. Yeah. Oh no. There is MLOpt. Maybe this is the one. We normally, if we want to do optimization, we use GitLab. So we program, we don't use the graphical user interface, and MLOpt, which is a C++ optimizer, which we like to use. But of course, you can use any C++ optimizer, but there's many different optimizers in this library. So sadly, the parameterization is not yet available in Rat, but it is on the to-do list for a future upgrade. So I'm happy to take more questions if there are any. Right. Can we visualize the direction of the electric current on the conductors? Yes. Does it follow the direction of the geometry path by default? Yes. Let me go back to Rat GUI. So by default, oh, where is my slides? I closed my slides, but by default, it will follow the direction of the path, indeed. Let's start from a solenoid, but there is a way. And now, I never used this before. There you go. Luckily, it's very clear. There you go. But you can visualize the direction of the current by going to View, toggle current arrows over here. And then you will see how the current flows. Yeah, you don't see it on the mesh because this one doesn't have current. That was just a structural thing. But if there is a coil, so let's go back to a simple coil toroid. And I say View, toggle current. All of these will have a tiny arrow for you to figure out in which direction the current is flowing. I think that is, yeah, direction of current and follow. But indeed, it follows the direction of the path. So it's the longitudinal vector in my slides that I will try to find back. Because if I place them back here, almost. Oh, back to the first, it's the longitudinal vector. Yeah, so this is the direction of current, which you can change with the reverse or with the flip. This is it's nice features. I hardly use them, but they can be very useful in some cases. That's a special transformation, but by default, it's just the longitudinal coordinate, and you can visualize those. All right. I don't see any or hear any other questions. So let's do the following, unless anything pops up. You should have all received a trial key for the Rat GUIs. There you go. Do you plan to have more trainings in the future? I plan to mostly have YouTube tutorials. So if you follow us on YouTube, you will stay up to date with the training, with the tutorials. Trainings like this, I will only do the introduction. So I will plan to do another one, but it will be the same one as this one in November. But not a training on a higher level difficulty, basically, for now. For more detailed training, then I upload tutorials so that I can do that once and yeah. Okay, you're welcome. All right. Anyway, so you should all have received a key to use the Rat GUI. If not, or if there's colleagues that you would like to invite to use the software, they can send me an email and I can send everyone a free 30-day trial. The trial starts on the first day you use your key for the first time. So if you don't have time today, that doesn't mean that your 30 days have started counting. They will start counting on the first time of use. It's a floating license model, so you can install the Rat GUI on as many computers as you like and use the single key on each of the computers. But the licensing server will take care that only one computer will be able to open Rat GUI at the same time. So that's how the floating license works. Yeah, any other questions, please feel free to send me an email about anything rat related or magnets related. Thank you very much for joining. I really enjoyed this training actually, so I hope you enjoyed it as well. Thank you for joining. A very nice day, and I hope to hear from you in the future.